award was established in 2002, and it's been recognised, the Early Career Award has recognised a long list of notable awardees who have exhibited outstanding achievements and exceptional potential in the field of structural science research, in the early stage of their independent careers. It's one of our most prestigious awards. It's given every year. That says something. Plus, we have this Etter Student Speaker Awards, also given every year, awarded from within SIG. So Peggy Etter's contribution to our field is critical, important, and awardees such as Ben, well deserved. Ben is receiving this award for his pioneering developments in the theory and practice of the magnetic pair distribution function method for studying short-range magnetic correlations in ordered and disordered magnetic materials. This is coupled with his outstanding leadership, mentoring, and service to the community, making him an exemplary recipient of this award. Today, he will tell us about when the tail wags the dog, also known as short-range correlations with long-range implications, a magnetic PDF story. With that, I'd like to present the award to Ben.
Thank you so much, Alan, for the kind introduction, and many thanks to all of you for being here in the audience. I'm truly, genuinely humbled and honored to be a recipient of this award. I look at the list of past awardees, and it is quite intimidating. I also recognize that there are many other wonderfully talented scientists who could very well be standing up here today, and I want to acknowledge that as well. So I feel wonderfully fortunate and honored to be a recipient of the Etter Award. Thank you for being here, and thank you for indulging my somewhat whimsical and certainly long-winded title. Thanks, Alan, for making your way through that long title. Hopefully it'll make sense by the end. Let me start off just by expressing my thanks to some of the many, many mentors who have helped me along my educational and career path. Starting as an undergraduate at Brigham Young University, where I did a research project with Grant and Campbell, and so it's his fault that I got hooked on structural science, and that it's been my passion ever since then. I'd also like to acknowledge one of my professors, Dr. Karine Chanel, who was very influential in my decision to go to graduate school, and a wonderful professor and mentor as well. And now that I'm back at BYU as faculty now, it's wonderful to work with them as colleagues as well. My graduate mentors, Simon Billings, whom many of you will know, and Tomo Uemura. He's not as well known in the structural science community. He does muon spin relaxation studies of magnetic materials, but it was Tomo who really helped me become fascinated with magnetism, and then Simon's experience with pair distribution function methods, and it was kind of the blending of those two fields that really sparked my graduate research, which has continued on through today. And then Bob Bergeneau, my postdoc mentor at UC Berkeley, just a brilliant scientist and a wonderful human being and mentor as well. And then, outside of my formal education, there have been so many others who have been mentors to me and examples and inspiration to me, whether or not they've known that. And I want to highlight just a few of them. Cora, who we all know here in the ACA, and Angus Wilkinson and Kate Page, among many others, but I would like to point them out specifically. And then really, the ACA as a whole, what a wonderful community to be a part of. I have so many wonderful memories and formative experiences at ACA meetings in the past. New Orleans, Kentucky, our virtual meetings even, during the COVID years, and then more recently in Portland and Baltimore. So many wonderful experiences, wonderful opportunities to meet people and develop new collaborations. YSIG, I've really enjoyed my time being involved in YSIG over the years, the materials, neutrons, and powder SIGs as well. Such a wonderful community to be a part of, and I'm grateful for that, and I'm grateful for the honor to be given this award from a society that has meant so much to me personally. I'd also like to acknowledge my wife, Shayla. You might tell from the more colorful background of her photo, she's not a scientist like the rest of us. She's a writer, not of scientific papers, but of short works of fiction and longer works of fiction as well, short stories and novels. But we've really enjoyed the experience of supporting each other through our educational and career paths to this point. So I'd like to express my gratitude to her as well. As for the scientific content of today's talk, I want to acknowledge my collaborators who have been involved, including my students at BYU, Raju Baral, who graduated with his PhD about a year and a half ago, Braden Jones, a master's student who graduated about 6 months ago, Christiana Zog, who was an undergraduate with me, who did really wonderful work as well. So I will highlight the work of all three of these students today. And then other collaborators include Omar Schmeissem and Elena Kuvyakina at Northern Illinois University, Emil Bozen, Alexandros Lapas, Brandon Campbell, Julie Staunton, and Rafael Herman have been wonderful collaborators on the projects that I will be presenting today. Should also point out where the experiments were done primarily at the NOMAD instrument at the Spallation Neutron Source. Many thanks to Jürg, Michelle, and Jua for their help with many experiments over the years, as well as at NSLS-2 on the 28ID1 beamline, where Melinda Abacon has been a wonderful collaborator and scientist as well. The funding for the research that I'll present today came from the U.S. Department of Energy. So, if I were to conduct a flash poll of all of you here in the audience today and ask you the question, why is structural science important? Then I would be willing to bet a not insignificant sum of monopoly money that the answers would mostly be along the lines of structure determines function, or structure-property relationships. That's what fascinates us. And I wholeheartedly agree. We need to solve critical issues facing humanity, and materials are going to be a big part of that. The properties that materials exhibit come from their structure, right? And so, that's why structural science is important. But what do we mean exactly by structure? Well, here we are at a meeting of the American Crystallographic Association. So naturally, the structure that most of us are talking about most of the time is this perfect, ideal, periodic, average crystallographic structure, right? And in my field, quantum materials, this comes up in the context of the coupling between different degrees of freedom in quantum materials. Charge, orbital, spin, lattice, topology. So the coupling between these different degrees of freedom can enable new and interesting properties and functionalities. An example of this would be multiferroic materials, where we have coupling between two or more of the primary ferroic orders. That could be ferroelectricity, ferromagnetism, ferroelasticity, or the antiferro orders as well that I'm including, where you can influence one degree of freedom through another. All right, and when we're talking about this type of coupling between degrees of freedom, the discussion usually begins with what the structure is, with what the ideal crystallographic structure is. So we'll talk about certain space groups that can or cannot allow ferroelectric order, for example, and therefore can or cannot be multiferroic materials. And this is all good, and as it should be. Understanding the average crystallographic structure is a necessary and crucial starting point for understanding the properties of any material. However, I am here today to talk to you not about this perfect average crystallographic structure, but the local structure, All right, the local structure, the correlations between atoms that are well defined on short spatial and temporal scales, but may perhaps average away to zero on longer scales. Here's an image produced by Thomas Proffen many years ago. It's been used in many talks, I'm sure. It represents some binary alloy with half the atoms being yellow and half the atoms being black. On average, each atomic site has 50% yellow atom, 50% black atom. Okay, and there's no long-range ordered arrangement of these yellow and black atoms. Nevertheless, if you look locally, there is clearly a preference for like atoms to cluster together. All right, so this would be an example of local chemical short-range order in some binary compound. A little more closely tied to what I'll be discussing later, how about local magnetic structure? Where now, instead of the correlations between atoms, we're talking about the correlations between neighboring spins, which again are non-zero, well-defined on local scales, but average away to zero on longer scales. For example, here we have some regions of ferromagnetically aligned spins. So if you look at any of these circled regions, then neighboring spins will have the same orientation or close to it. But if you go further away, it's essentially random. And these locally correlated regions are random with respect to each other as well. So the average, there is no long range, crystallographic magnetic structure here, but there's clearly some local spin correlations. All right. The point here is local is often not equal to average. The local structure often has important differences from the average structure, which are going to impact the properties of the material. Right? So, understanding the local structure can have very important implications, or failing to understand the local structure can lead to undesired outcomes. So, to try to emphasize this point, here's an example. Not my own work, but relaxer ferroelectrics. These are materials with remarkable dielectric and piezoelectric properties, and they have some cation disorder, as we see here, and they behave a lot like ferroelectrics, but with some glassy behavior as well. And they're very useful. They can be used for high-performance piezoelectric devices and many other applications. And it turns out that many of these interesting properties can be understood as a consequence of an idea called polar nanoregions. All right, these are nanoscale heterogeneous regions with some non-zero local electric polarity, but there's no long-range locking in of all of these different polar nanoregions. Okay, they may not necessarily be correlated with each other. All right, and the response of these nanoscale heterogeneous regions to external fields, external stimuli, has been used to explain many of the properties seen here. So this is one well-known example of where the local structure can determine and be the origin of very useful physical properties in the material. So to really hammer this point home, short-range correlations that define the local structure of the material are often overlooked or incorrectly considered to be perhaps, interesting, perhaps curious, but ultimately unimportant. But I'm here to say that often these short-range correlations can be key drivers of material properties. All right. Those of you who are terminally online, you've probably seen this meme before. We have some tiny little domino right here. You knock it over and eventually it knocks down this gigantic domino here. So nanoscale correlations of the local that define the local structure. You tip that domino over and it's going to influence your macro scale behaviors in materials. All right? Or said another way, the tail can wag the dog. Something seemingly small and insignificant can have a profound effect on the larger system. All right. So, here's the outline of my talk. I will introduce magnetic PDF analysis as a way to study local magnetic structure. And then I'll give 3 examples of local magnetic structure wagging the dog. All right. The first will be the magnetovolume effect in an antiferromagnetic semiconductor, manganese telluride. Then we'll look at a multiferroic material, strontium, barium, manganese, titanium oxide. And finally, a frustrated magnet, geometrically frustrated magnet, sodium manganese oxide. And I've chosen these examples from our recent work, not necessarily because they're the highest cited projects I've done or even the most significant or anything like that, but I think they really highlight clearly this point that I'm trying to make, that the short range correlations, which you sometimes have to work hard to observe, can have profound influences on the macroscopic properties. Okay, so hopefully I've convinced you that local structure is important. How do we study it? We can't just look at the Bragg peaks, because that just gives us the average structure. So we have to look at the diffuse scattering. One popular way to do this is the atomic pair distribution function method, PDF. So here's a quick refresher. It's a total scattering method, and we're utilizing the Bragg and diffuse scattering. It gives us information about the average and local structure. Typically this is done with a powder sample, do a scattering experiment, and the key thing is to collect our scattering pattern out to a large momentum transfer. This is 25 inverse angstroms shown here. So that we can then do a Fourier transform into real space to yield the pair distribution function. All right, so now the horizontal axis here is real space distance in angstroms, and peaks in our PDF. That means that there's a high likelihood of finding two atoms separated by that distance. All right, so we have moved from momentum space into real space, and this is giving us a map of the local interatomic correlations in our material, regardless of the long-range average periodicity of the crystal structure. The local structure is represented here in the PDF. So that's the atomic PDF method, which is well known, well established for looking at local atomic structure. What about magnetic PDF? Well, it's the exact same idea. So the scattering, and we're going to talk about neutron scattering today. So neutrons scattering from nuclei, you Fourier transform that scattering pattern and get the atomic PDF. On the other hand, if you just look at the intensity of neutrons being scattered from the magnetic moments present in a material and do the Fourier transform, that will give you the magnetic PDF. In many experiments, we're actually collecting a combined nuclear and magnetic scattering signal. So that will give us a combined atomic and magnetic PDF with the signals mixed together in real space. So luckily for me, 10 or 12 years ago, no one had yet worked this out. People knew that the magnetic PDF should be a thing, but no one had really worked out the details. So that became a big part of my PhD project, working out the details of magnetic PDF. And it's, in the end, a straightforward analogy to atomic PDF. You start with the magnetic differential scattering cross-section. This is expressed here just in terms of magnetic moments and their orientations and positions, not assuming anything about periodicity. And you just divide by the squared magnetic form factor, you compute the Fourier transform. The details are not so important, but you end up with an expression that looks like this, a nice closed form expression. And it has a series of delta functions which occur at the distances separating pairs of spins. It also, and this is very similar to what we get in atomic PDF. It also has a term that's linear in R. This is kind of a strange term. It's linear in R, and then it actually turns off at distances beyond the spin pair separation distance. So this is not in atomic PDF. This is something new. And then there's this additional baseline term which is related to the average net magnetization of your material. But anyway, these features here, the peak and the baseline slope, their sign and strength are determined by the local spin correlations, which are encoded by these coefficients A and B. The A coefficients give information about the transverse correlations between a pair of spins, transverse to the direction joining those two spins, and B contains information about both the longitudinal and transverse correlations. These details are not so important because when you actually use this expression to calculate the magnetic PDF for some given magnetic structure, it's very intuitive. This is the nice thing about magnetic PDF. So let's say we have a one-dimensional chain of spins that are aligned with each other. The magnetic PDF is just a series of positive peaks, all right? And the first peak here occurs at the nearest neighbor distance, the second peak at the second nearest neighbor distance, and so on and so forth. And there are positive peaks because the spins are aligned with each other. If you have an antiferromagnetic chain, where we have alternating spin directions, then we have alternating negative and positive peaks in our magnetic PDF. So it's a really nice intuitive function. You can look at a glance and know what the local magnetic correlations are in your material. Okay? And again, whether or not this is a long-range ordered magnetic state or these are short-range magnetic correlations, we are looking on the local scale here, so we'll be sensitive either way. Here's another example, a simple cubic antiferromagnet. You look at the nearest neighbor correlation here, which is opposite alignment between our spins. And so the first peak here is negative. The second nearest neighbor, we have parallel alignment, so the second peak is positive, and so on and so forth. Okay, so that's magnetic PDF in theory. How about in real life? How do you actually do this? Well, you can just do a standard neutron PDF experiment, not knowing anything about magnetic PDF, and in fact this has happened in the past. People have collected magnetic PDF data without their knowledge, because you just do a regular neutron PDF experiment, and if it's a magnetic material, your magnetic PDF will be included in your data. Whether or not you were looking for it or even wanted it, it will be there. Another way, you don't have to do a specialized PDF experiment, just any neutron scattering experiment. And then if you can find some way to isolate the magnetic component of the scattering, then you can Fourier transform that and get your magnetic PDF that way. Turns out that option 1 here has been used more frequently, and it works quite well actually. So for the PDF community, this is the easiest way to enter into magnetic PDF land. In the meantime, we have some software out there now to help with magnetic PDF analysis as well. So the tools are in place. The experimental methodology has been established. We have software tools in place to do this. The first magnetic PDF experiment that we ever did was on manganese oxide. This is an antiferromagnetic material. It undergoes a long-range magnetic transition below 118 Kelvin. So below that temperature, we have this long-range antiferromagnetic order where the spins within shared 1-1-1 type planes are aligned with each other, but between alternating planes, the magnetization is reversed. Okay, so it's an overall antiferromagnetic structure. Turns out that there's also a rhombohedral contraction of the lattice along the 1-1-1 direction when the material undergoes that magnetic transition. Happens to be the first material that whose magnetic structure was ever determined by neutron diffraction. That was the work of Cliff Scholl in 1951. So kind of fun for us to revisit this historical material in the context of magnetic PDF. So my first ever neutron PDF experiment was done on manganese oxide at Los Alamos at the mPDF instrument, which unfortunately is no longer available to the community. And this is the data we got. So here's the PDF data, and what I've done here is just a simple fit using the atomic structure of manganese oxide, the well-known atomic structure, this rock salt structure. And this is the fit residual. And it looks like something has gone horribly wrong. However, I was thrilled when I saw this, because this does not mean that our sample was bad or the experiment was bad. This just means we have a gigantic magnetic PDF signal, which is not included in the atomic PDF. So the red line showed up here, that I'm showing up here, that was produced by just including the nuclear, the atomic correlations in the model. But of course that leaves out the magnetic PDF. So whatever magnetic PDF signal is in there will show up in this fit residual. And this is clearly a very structured fit residual, so there's something in there. And we have an expression for the magnetic PDFs. And we know the low temperature magnetic structure of manganese oxide, so we can just calculate the magnetic PDF, and it fits perfectly. So here we are zooming into that fit residual, and the red curve here is the magnetic PDF. So this was the first magnetic PDF fit. It worked. It was a huge relief that I didn't make any mistakes in the math, It worked out. Now, it wasn't very groundbreaking to determine what the low temperature magnetic structure of manganese oxide was, because that had been known for 60-something years. But what was more interesting was looking above the nail temperature, where there is no long-range magnetic structure, but there are nevertheless short-range correlations. Oh, let me explain this first. So often we'll show magnetic PDF data in the form here, where we have our total PDF signal and our total PDF fit. That includes both the nuclear and magnetic PDF up here. And then this is just the isolated magnetic component right here. Okay? So this is the magnetic PDF part of our overall signal. And then this is the overall fit residual. So it worked. Very, very good. But more interesting was to look at the magnetic PDF signal above the nail temperature, where there were no longer any magnetic Bragg peaks in the scattering pattern. There was magnetic diffuse scattering, of course, all right, because we do have short-range magnetic correlations. But now we can look at those short-range correlations in real space. And so here's the magnetic PDF, these little wiggles going all the way up to room temperature, and I won't go into the details right now, but we could actually learn something interesting about manganese oxide, about the exchange interaction between neighboring manganese atoms. In collaboration with theorist Julie Staunton, we were able to learn something about manganese oxide because we had access to these short-range correlations that persist in the paramagnetic state. When the average magnetic structure has disappeared, there are no long-range magnetic correlations at those temperatures. Nevertheless, these well-defined local correlations contain important information about the material. Okay, so this was our first foray into magnetic PDF analysis, and it worked well enough that I was willing to try to make it a significant part of my career going forward, and luckily that has more or less worked out. So in the meantime now, we've looked at many other materials with magnetic PDF analysis, and other groups are starting to do it as well, which is really gratifying to see. So you know, magnetic PDF, it's a real thing now, and we can actually learn something interesting about magnetic materials using this method. So let me illustrate that through 3 examples. The first one, looking at the magnetovolume effect in manganese telluride. So manganese telluride is one of my favorite materials at the moment, at least. It's useful and interesting for a number of different reasons in the context of thermoelectrics, altermagnetism, spintronics. What I'm going to talk about today is the aspect of magnetostructural coupling that we've looked at in manganese telluride. So here is some representative magnetic PDF data on manganese telluride. Here at 100 Kelvin, below the magnetic ordering temperature, we have a nice, strong, long-range magnetic PDF signal because we have long-range magnetic order. Okay, we've got a great fit to it. At 320 Kelvin, which is above the ordering temperature of 307 Kelvin, we still have very clear wiggles in the magnetic PDF channel down here, but they die out after 15 angstroms or so. So this means we have short-range magnetic correlations, which we can very clearly see in our data, that are persisting into the paramagnetic state. All right. So by collecting magnetic PDF data at many different temperatures, we can look at the evolution of these short-range magnetic correlations. We can pull out the correlation length, for example. So here's the correlation length in the plane as well as out of the plane at various temperatures, which we extracted from our magnetic PDF fits. It's interesting to note that the out-of-plane correlation length tends to be systematically a bit longer than the in-plane correlation length. It was interesting to me that we were able to observe that even from powder data, where you might think that this directional sensitivity has been lost. But we were actually able to pull that out pretty robustly, and that makes sense in terms of the magnetic exchange interactions in manganese telluride. But clearly you can see here that below about 350 Kelvin, there's a strong, a rapid increase in the correlation length as we are approaching the long-range ordering temperature. Above 350 Kelvin, we have relatively short-range but stable magnetic correlations, persisting up to the highest temperature we measured, which was 500 Kelvin. By the way, if you're skeptical that we could really pull out a meaningful difference between a correlation length along the c-axis versus in the AB plane, we also did 3-dimensional magnetic PDF analysis on a single crystal of manganese telluride. This right here is a real space view of the local magnetic correlations in manganese telluride at 330 Kelvin. So the bright spots mean parallel alignment, the dark spots mean anti-parallel alignment. And you can see this is the XZ plane, so it's kind of like looking at this face right here. Whereas we move along the C axis in the Z direction, we alternate between up and down spins. So we see these alternating colors, but within the plane, the spins are aligned with each other. So we have the same color within the plane. And in fact, we can change our view and actually look at the 3D magnetic PDF in the plane, and we just have this nice hexagonal arrangement of bright spots, because within any given plane, the spins are all aligned with each other. So this is really neat. We can really view these correlations, these local magnetic correlations, directly in real space, even in 3 dimensions if we have a single crystal available. But what you'll notice here is the correlation length along C is noticeably longer than it is along in the AB plane. All right, and we can in fact take these line cuts and fit a correlation length and all that. And our single crystal data ended up being very, very similar to what we got from our powder data. So that was nice to see that agreement. What I'd like to show you now is, in addition to the correlation length, we can also pull out the local magnetic order parameter. So I'm showing you right here the average magnetic order parameter. So this is what you would get just from integrating magnetic Bragg peaks, for example, okay, or doing traditional Rietveld refinement, including the magnetic phase. And this magnetic order parameter drops down nicely to 0, right at the expected nail temperature, so it looks great. There are no long-range correlations above the nail temperature, so it's 0. On the other hand, if we look at our magnetic PDF data and perform our analysis just up to, the first 20 angstroms. Okay, so we're looking on a 2 nanometer length scale. And we fit our magnetic PDF model to the data to get these little wiggles out. Then we can pull out a local magnetic order parameter, which looks a lot different. So here's the local magnetic order parameter, these blue triangles. It does not disappear above the nail temperature because we still have local correlations present. All right. So this is really highlighting the difference between the average and the local structure, magnetic structure. The magnetic correlations are very much alive and well above the nail temperature, with a significant ordered moment at the nearest neighbor distance of about 1 Bohr magneton. All right. So we have well-defined correlations that extend with a correlation length of, extending over a few near neighbors, with a net correlated moment of about 1 Bohr magneton, persisting well into the paramagnetic state. All right, what does this have to do with macroscopic properties? Well, I'm showing you here the unit cell lattice parameters determined from X-ray diffraction. And you may notice that there's a kink in the, we've got the typical thermal contraction here, and then it dips below the high temperature linear trend. Okay, it seems to be anomalously contracting around the magnetic order of temperature, marked by these blue lines right here. Okay, this is called spontaneous magnetostructural, changes in the dimensions of a material in response to the development of intrinsic magnetic order. So manganese telluride is showing this magnetostructural behavior. And if we look at the volume, here's the unit cell volume right here, we can actually calculate what we would expect the volume to be as a function of temperature using a Debye-Gruneisen model. And that's shown by the black curve right here. So this is what we would expect. Based on the high temperature linear trend here, in the absence of magnetism, we would expect this black curve right here. Okay. The difference that you see here is evidence of the magneto-volume effect. Okay, we're changing the unit cell volume because of the magnetism. You may notice it starts above the nail temperature, right? The blue line here, this is 307 Kelvin. This is where the long-range magnetic correlations kick in. And yet, the deviation from the non-magnetic expectation begins well above that temperature. Okay, we can plot the fractional volume change, okay, delta V over V, for both a pure compound and a sodium-doped compound, which I won't talk too much about today. But again, this is highlighting that this anomalous contraction of the volume begins well above the long-range nail temperature. Okay, So this is direct evidence that the short-range magnetic correlations are driving this macroscopic property, the unit cell volume, which is pretty cool. By the way, this happens to be an extremely large magnetovolume effect. This is almost 1%, okay? It's, negative 8 times 10 to the minus 3. Other kind of classic antiferromagnetic, magnetostructural materials are an order of magnitude or more smaller, generally speaking. Okay, so manganese telluride happens to have the largest known spontaneous magnetovolume effect for any antiferromagnet, which was cool. We just stumbled across that. What's maybe more interesting to me is to compare more quantitatively the information about the local magnetic structure that we have from our magnetic PDF analysis. Here's the local magnetic order parameter, LMOP, okay, it's the acronym for that. Here's the correlation length. Compare these local magnetic features with this average structure behavior of the unit cell volume, and they actually line up remarkably well. So I'm showing you here on the left vertical axis, this is the volume change. I've actually made it positive just for ease of comparison. And on the right vertical axis, I'm showing the local magnetic order parameter. They lie right on top of each other. And in fact, if you plot one versus the other, the fractional volume change versus the local magnetic order parameter, we have a very clear linear relationship, okay? I want to emphasize, these points down here represent magnetic PDF data collected in the paramagnetic state, where no long-range magnetic correlations exist. So this linear trend begins with short-range correlations in the paramagnetic state, already driving this long-range change in the unit cell volume of the material. So the linear coupling between the lattice strain and the local magnetic and the magnetism occurs to the local magnetic order parameter. No long-range order is required. Okay, so forget about your average crystallographic structure. All we care about is the local short-range magnetic correlations in this case. So that's the example of manganese telluride. Let me check my time here. Okay. We see similar behavior, but in a very different context. In strontium, barium, manganese titanium oxide, a multiferroic material. It has this pseudo-cubic perovskite structure. And if you put enough barium into the strontium site, then you can drive it from this cubic paraelectric structure into a tetragonal ferroelectric structure. All right? And it also develops antiferromagnetic order at low temperature. So this region right here represents a multiferroic state, all right, where we've got ferroelectricity coexisting and as we will see, interacting with the antiferromagnetic behavior. So here's some of the early evidence of multiferroic behavior in this material. We're seeing here the A and C lattice parameters, all right? So in the cubic state, of course, A is equal to C. But then below the ferroelectric Curie temperature, A and C split, okay? And then at lower temperature, the antiferromagnetic order kicks in. And we see that there's a strong response in C over A to the development of the magnetic order, all right? So C over A, that ratio is proportional to the ferroelectric moment, all right, the net electric dipole moment, I should say. And so, so C over A decreasing in response to the development of magnetic order, that is evidence of this magnetoelectric coupling, so the interaction between the ferroelectric behavior and the antiferromagnetic behavior. So this is the multiferroic nature of strontium, barium, manganese oxide. All right. We can also see something similar in the dielectric constants here. What you might notice, though, is that this C over A ratio and this dielectric constant begins to show a change well above the nail temperature. So here's the nail temperature, about 200 Kelvin. Around 300 Kelvin, the C over A ratio turns over. The C lattice parameter turns over, all right? And yet, this C over A ratio, that change is supposed to be, the evidence of the multiferroic behavior in this material. So again, this is just indicating that this multiferroic behavior begins even when we're not in the long-range ordered antiferromagnetic state, okay? Let's prove that more directly by looking at magnetic PDF data. Here's our neutron PDF data for one of the compounds that we looked at. The magnetic PDF signal is actually very small. If you're not looking for it, you won't notice it. So you have to work kind of hard to find it, but if you do work hard and you believe that it's going to be there, then you'll find it. That's not always true, but in this case it was true. We have a small but unambiguous magnetic PDF signal. So that's good. That means we can look at how these magnetic correlations change as a function of temperature in this compound. And we can play the same game that we were playing with manganese telluride, where we do these fits, we pull out a local magnetic order parameter, a correlation length, and so forth. Okay, so the results of our PDF analysis, we're looking at the lattice parameters. So C is the upper branch, A is the lower branch, and these are the difference between blue and red. These are two different fitting ranges that we used in our PDF analysis. I won't go into that too much. But we're sensitive to these changes in the lattice parameters, which again represent the ferroelectric behavior. The larger the C over A ratio, the greater the electric dipole moment. And then here we have the local magnetic order parameter determined from our magnetic PDF fits. The key observation here is that those correlations, the local magnetic correlations, do not disappear above the nail temperature, but instead persist into the paramagnetic state. So let's look at those together. Here's the C over A ratio. Here's the local magnetic order parameter. The C over A ratio begins to turn over, which again, that's our evidence for the multiferroic coupling, the multiferroic behavior, as soon as the short-range magnetic correlations are kicking in. Okay? So let's do the same thing where we plot C over A minus 1 versus this local magnetic order parameter. A nice negative linear correlation. So again, this is that multiferroic behavior where the development of magnetic correlations drives a change in the electric polarization. All right, in this case, decreases the electric dipole moment. And these 4 data points were collected in the paramagnetic state. All right, there was no long-range magnetic order. So what's the conclusion from this? The conclusion is the electrons don't care about the global magnetic phase. The electrons do not care if you have long-range antiferromagnetic correlations or not. They are responding to their local environment. The short-range magnetic correlations that are present. The local environment dictates the multiferroic behavior in this compound. Okay, very similar to what we saw for manganese telluride. All right, one more example. Nanoscale degeneracy lifting in sodium manganese oxide. This compound is an imperfect, frustrated triangular lattice. So geometrical frustration in magnetism, this is the idea that most easily represented by a triangular lattice of spins that want to be antiferromagnetically aligned. How do you make spins on a triangular lattice all be mutually antiparallel? You can't, all right, unless they can be non-collinear, but let's just assume Ising spins. You can't do it. Okay, so that's frustration, the essence of geometrical frustration. This material, sodium manganese oxide, has triangular lattices, has these sheets of triangular lattices of manganese atoms, but they're not perfect equilateral triangles. One of the bonds is shorter than the other two, so it's an isosceles triangle. So R1 is shorter than R2, which is equal to R3. All right, we have these manganese 3 plus spins on each site. All right, and so the geometrical frustration is partly relieved because the exchange interaction between these two atoms, these two spins, will be different than the exchange interaction between this pair and this pair. But we still have this one remaining degeneracy. R2 and R3, they are equal to each other, those bonds are equivalent. So J prime, this other magnetic exchange interaction, is equivalent between these two pairs of spins. So how do you establish long-range magnetic order? Well, that's an interesting question because this material does undergo a transition to long-range magnetic order, to a stripe-ordered phase, where somehow we've chosen R2 or R3 to be different from the other, all right, and J prime, therefore, to be different than a J double prime, for example, okay? How do we do that? Well, in the sister compound, copper manganese oxide, there is a long-range structural transition from a monoclinic structure, which has this degeneracy of the R2 and R3 bonds, to a triclinic structure, where that symmetry is explicitly broken. Sodium manganese oxide has no such structural phase transition. It remains monoclinic in the average structure to all temperatures, down to the lowest measured temperatures of, Kelvin or so. And yet there's this stripe order which appears to break that symmetry. So what are we missing here? Well, we looked at this with PDF analysis, and what we found was that the sodium manganese oxide compound at low temperature is better described by a distorted triclinic model rather than the long-range crystallographic monoclinic model, okay? So this is just showing the fit residual. We've got smaller wiggles here for the triclinic model. So that means locally, sodium manganese oxide actually is triclinic, has this lower symmetry in the local structure, okay? And we can look at the temperature dependence of that, and it turns out that this local triclinic distortion becomes more pronounced below about 150 or 200 Kelvin. Okay, and we can compare the goodness of fit between the triclinic model, the monoclinic model. These details are not so important, but the point is, the PDF data indicate that there is a preference for local triclinic distortions on a length scale of about 25 angstroms that grows below about 150 Kelvin. Okay, so at low temperature and short length scales, the local structure of sodium manganese oxide is triclinic. And this is significant because the triclinic distortion results in all three of these triangular legs now being different from each other. So we have fully lifted the degeneracy of these magnetic interactions, and that should allow magnetic order to develop. But to really pin that down, let's look at the magnetic correlations, so magnetic PDF analysis. So here I've isolated just the magnetic component of the neutron PDF data. At 5 Kelvin, we have a nice long-range antiferromagnetic ordered state. And we know that it's long-range because these wiggles are persisting out to large distances, whereas at 50 Kelvin, above the ordering temperature of about 44 Kelvin, we have only short-range correlations, okay? But nevertheless, these short-range correlations persist. They are there in the paramagnetic state. So we can look at the temperature dependence of the correlation length, of the local magnetic order parameter, all of these things that we've done before. And what we see is that the correlation length, it's really restricted just to kind of the nearest neighbors at the highest temperatures. But as we lower the temperature, naturally, those correlations grow in spatial extent. Okay, so the correlation length increases and is appearing to diverge, okay? When it gets to about 25 angstroms, that's when the long-range order kicks in. And then we get true, genuine magnetic Bragg peaks and long-range antiferromagnetic order, okay? And this is what the local magnetic order parameter is doing right here compared to the average magnetic order parameter. So let's compare the temperature dependence of the structural distortion, that local triclinic distortion, and these local magnetic correlations. We see they share a very similar temperature dependence, right? It's right around 150 Kelvin that the correlations, which had plateaued at kind of the nearest neighbor distance, now begin to grow beyond just the nearest neighbors, all right? That's the same temperature where this local triclinic distortion begins to grow in magnitude, all right? So this suggests some interplay between this local triclinic distortion and the growth of these antiferromagnetic correlations. If we remember that the length scale of the local triclinic distortion was 25 angstroms, and that was relatively independent of temperature. So we have these 25 angstrom kind of puddles of triclinic distortion, local triclinic distortion in our structure. Well, as soon as the antiferromagnetic correlations reach that length scale, 25 angstroms, that's when the long-range order is triggered, okay? 25 angstroms right here, boom, we move into the long-range ordered magnetic state. So what does this mean? This means that the local triclinic distortion allows the growth of those antiferromagnetic correlations within that distorted triclinic region. And then as soon as those magnetic correlations have a long enough length scale to bridge these different locally distorted triclinic regions, that's when long-range magnetic order is triggered. So this is an interesting transition mechanism for a frustrated magnet. We have a short-range triclinic distortion lifting this triangular degeneracy on the nanoscale, enabling long-range antiferromagnetic order once the length scale of the magnetic correlations matches the length scale of that local triclinic distortion. So in this case, it's a local structure effect, which is driving a long-range magnetic effect. In the other two examples, it was a local magnetic effect driving a long-range structural effect. So it's really interesting to me that we can see it go both ways in various materials. So let me wrap up here. We've looked at 3 different examples. We've looked at manganese telluride, where short-range spin correlations drive a giant lattice contraction. And that giant lattice contraction proceeds uninhibited by the transition into the paramagnetic state. It just continues its merry way along. It doesn't care what the long-range order is, just what the local magnetic correlations are. We saw in strontium, barium, manganese, titanium oxide, once again, that short-range spin correlations can facilitate magnetoelectric coupling in a multiferroic material. And then in sodium manganese oxide, short-range structural fluctuations trigger long-range antiferromagnetic order. So these 3 examples together, to me, demonstrate a point which is actually quite obvious, which is that local interactions respond to local structure. And yet, they can drive global behavior. So, in the end, this should not be so surprising that short-range magnetic correlations can, even when they do not translate to long-range magnetic order, or short-range structural fluctuations that do not lock into a long-range crystallographic phase transition, are nevertheless able to influence electrons that are interacting through local interactions. And in the end, in these examples, and in many others that we've encountered, these local interactions are crucial for the global structure property relationships that we're interested in. So thank you very much for your time. Here's a list of other references and papers where we've explored similar ideas. The underlying ones are the ones I highlighted in this talk. Thank you so much for your time and for your support, and I'm happy to answer any questions you may have.
Do we have any questions from the audience? That's honest.
Thank you for the talk. I had a question about how you separate out the magnetic PDF from the atomic PDF, particularly when you're going through a phase transition. Typically, if we see a deviation from a structural model, we might think it's a structural distortion. Same with the sodium manganese oxide, where you see a triclinic structural distortion. If I see a deviation, how do I know whether it's magnetic or structural?
That's a great question. Let's look at a typical magnetic PDF pattern. Let's see, I'm going to go back to manganese telluride because it's a really large magnetic PDF signal that kind of hits you in the face. But this demonstrates it well. So the total PDF has really sharp peaks at distances corresponding to pairs of atoms. And this is a fairly crystalline material. If this were an amorphous material, it would look a lot different. Nevertheless, for a good crystal like manganese telluride, the atomic component of the PDF consists of these very sharp peaks. If there's a structural transition and your model isn't capturing that correctly in the PDF data, you will see sharp wiggles in your fit residual. Okay? Compare that to the magnetic component. It's very, very broad, and there's a reason for that. It has to do with the magnetic form factor, and we haven't properly deconvoluted our signal from the magnetic form factor. So we end up getting a much broader magnetic PDF signal, which on the one hand, it's frustrating because it means we're losing real space resolution about the local magnetic correlations. On the other hand, it means the magnetic PDF signal is very recognizable, very distinct from problems with your nuclear model. Because we have these kind of long wavelength broad features, whereas if you have, if there are local structural distortions that you're missing in your structural model, they'll show up as sharp features. And in fact, you can kind of see it right here. See this sharp wiggle right here? That's because at high temperature manganese telluride, there's a funny distortion, local distortion that happens between the manganese and tellurium atoms. Actually happens in a lot of other binary thermoelectric compounds as well. But you see a sharp feature localized right on the nearest neighbor distance, nearest neighbor manganese tellurium distance here. That is not easily confused with these broader features of the short-range magnetic correlations. So in practice, it works out really well as long as you have a fairly, crystalline material. Amorphous or very poorly crystalline materials, then it gets a little trickier. And your best bet is to use a technique like polarized neutron scattering, where you can actually directly separate nuclear and magnetic contributions to the scattering. Thanks.
Can I take you back to your magnetic order parameters where you're comparing the average and the local magnetic moments? Can you put that slide up?
Yeah.
How should I think about the reduction of the moment? There are a few different ways I could do it. One is that less alignment between the spins. Another could be if we had band magnetism, we had less of a moment developing. And the third may be that electrons are moving between orbitals, and if you have some orbital occupancies changing as you might for an ionic manganese, that might necessarily and easily explain the structural distortions that can occur. So can you comment a little bit what's known about the loss of the moment, and do you have an understanding of what the origin is?
Sure. So in the materials that I've shown today, to a very good approximation, the local moment is constant with temperature. Okay? So we don't have a significant change in the bare local moment as a function of temperature. So the reduction of the magnetic order parameter, whether that be the average magnetic order parameter or local, we are interpreting in terms of misalignment of the spins. Okay? Band magnetism isn't relevant in the materials that we've shown today, although there are some interesting possibilities with that. But we are interpreting this primarily in terms of just the degree of alignment between bare local moments that have a fixed magnitude. Yeah. And it seems to work pretty well on the basis of calculations using a somewhat sophisticated DFT approach, which I can't claim to understand. Julie Staunton has worked on this. It's distorted local moment approach, and it seems to be very consistent, even quantitatively so, with what we're observing in our magnetic PDF data.
And does that theory also capture the lattice changes? Does it also predict really large?
The theory, no. So her theory did not include that possibility. But the reason for this very large lattice change in manganese telluride, you can actually, just by simple energy balancing arguments between the elastic energy cost of contracting your lattice and the energy savings that you get by having favorable magnetic exchange interactions, you can get a good order of magnitude estimate for the volume contraction that we saw. So just pretty simple energy arguments will get you that lattice contraction.
Great, thank you.
One more question.
Yes, I was just curious, what about the crystallographic information file allows you to fit magnetic PDF?
So a standard SIF, you won't be able to get a magnetic PDF without inputting some additional information. So that type of information is, for example, the magnetic propagation vector or vectors, the basis vectors, and so forth. It turns out that the magnetic SIF file, the mSIF format, has all that information, and it also has the structural information. So if you are working with a system that has an mSIF on the MAGN database, for example, then you can load that into the software that we've developed, and it can give you your magnetic PDF and your nuclear PDF together. So, but otherwise, I think there are, about 2,000 magnetic structures on the database right now. So a lot, but it's certainly not comprehensive. So if you are working with SIF files, then there's a little more work that needs to go into defining your magnetic structure in relation to the atomic structure. If you are interested in that, please talk to me. We have a lot of tutorial materials to help you figure out how to do that.
Any more questions from the audience? If everyone would join me in thanking and congratulating you.